the title slide now, Mike.
Okay, thanks. So let me just go on to the first slide, and that is what exactly is a problem. In math and physics, it would be defined as some inquiry starting from given conditions or axioms to investigate or demonstrate some fact, result, or law. The solution here would be a proof or some sequence of mathematical actions that might indeed show the law. In AI and planning, and indeed in our own cognitive systems community, we define a problem usually as some initial state and a goal state, along with some background knowledge that allows us to create a solution in terms of a plan that would be a sequence of actions that will get us from the initial state to the goal state. But if you look at Google and look for a definition, you'll find something that's a little closer to what I'm struggling to capture. This is the notion that a problem is some situation regarded as unwelcome or harmful, needing to be dealt with or overcome. And so that is close. What I want to do to operationalize and define this a little clearer in computational terms is to define it as some situation that limits the agent or cognitive system's choice in terms of potential goals or available actions. And through this talk, I'll try to take this apart and refine that till I'll include some examples in an implemented system, but I wanted to emphasize that today I'm really trying to look at fundamentally what does it mean to for a cognitive system to have a problem, and how would you represent that? So I'm going to also start by giving you my conclusion so you know where we're going, especially if we don't quite get to the end. I'll at least be able to show you that the main points are that the problem with problems, as I see it, is that this classical representation can be arbitrary and is assumed to be given by some human or external system, rather than recognized by the cognitive system itself. The alternative that I'll present now, I will mention up front, is mainly theoretical and has a formal notation and a few examples, but I'm trying to re-examine fundamentally what we mean by a problem, rather than to present today in my work solutions with empirical results. And then finally, I challenge the community to look at that. We all, in some form or another, touch on this problem of what is a problem, how do we represent, and how would a system represent. And I think that we need to re-examine the assumptions that we've held for many, many years. In this outline, we'll first look at the classical representation of a problem. I'll provide the notation and representation of my alternative. I'll look briefly at a couple example implementations, and then I'll conclude and reiterate this challenge. So there are a number of different kinds of problem solving. Often we see puzzles, and I question whether they're actually problems in terms of at least a threat or restriction to an agent. But there has been a lot of work on, for example, the 8 puzzle problem and variations on that. In the design community, a solution is some configuration of components that meet a given functional requirements for some artifact that you're trying to design and then build. Bridge design would be an example of this. And then in planning and execution, the solution is a sequence of actions or a plan that will then achieve a state that entails this goal. Examples are tactical military problems, and an interesting one is MacGyver problems, talked about by Scheutz in his lab, Matthias Scheutz and others. It's very interesting how their take on that, and it's a little closer to what I'm trying to get to here. Classically, we look at a problem P as a triple, where you have sigma, the state transition system, S naught, a goal, an initial state, and then some goal G. The state transition system is itself a triple, including Capital S, all possible states, all possible actions A, and a function gamma, which represents a successor function. That is, given a state in action, it returns the following or successive state resulting from the execution of that action. This is also recursive, as you'll see below, but a problem then is simply a sequence of actions, alpha 1 through n, and we will also be able to index the planned with a notation that looks like array notation to say what subsequences. So here we have alpha 1 is the head, the tail is the rest 2 through n of the actions in the sequence. So gamma can also be thought of recursively, so that starting from some initial state and given a plan, you recursively execute gamma on each successive state, and you end up in some goal state that entails the goal expression. We say entails here instead of being a subset of the final state because it could be abstract. We might want to have some block on block B. So there could be a number of states that would entail that goal. This is pretty straightforward. I borrowed that notation. And in the blocks world, their really problems are arbitrary. We stack A on B for no apparent reason. It's unclear why the starting state was less valued than the final state of having A on B. It's just some arbitrary state that we want to achieve from some other previous state. And we generate some plan or sequences of actions that executed will get us there. On the other hand, we might think of a modified construction domain where to stack the triangle D on A, the tower AB, would be to keep the water out of some house. So that there's a reason that you want to put D on A to perhaps keep your possessions dry and the house safe. That is lacking in most problems as they're defined. There's really no causal reason that the initial state is a problem and that the goal state is a solution. Sometimes you'll use utility to indicate that initial states are of less utility than the final goal state. But the reason why one state is problematic, the state that you're in or the initial state, is implicit, and you can't really explain that. The system can't reason about that well when things start to go wrong. And then finally, it requires human input, which is a restriction. I think it's very interesting, where do goals come from and how do agents recognize problems? The alternative that I propose then is to define a problem as some situation that limits choice in terms of potential goals or available actions. Here I'll differentiate between potential and kinetic goals. Kinetic goals being those that are in the agent's current agenda that we're trying to pursue, that we're building plans for and executing plans to achieve. Potential goals are those that we might want to have in the future. So an example would be the neighbor that moves in next to me and trashes his yard and his house. My property value tends to fall in such a state, and that situation means that if I choose to have my house sold, even though I don't currently have the goal to sell my house, that would be limited. It would be harder to choose that goal into the future, given this messy neighbor. Another example would be a worker with old skills where new technology comes along and he does not have the skills to be able to compete and maintain his job. So that would require learning new action models, for instance, increasing the set capital A of the kinds of actions that the agent would be able to achieve. So it's a problem for a worker when new technology comes along and there's a reason that you could specify for that. And then you give such an explanation about what is limiting. You could then choose the proper goal yourself, that is the agent. So to be able to represent this, I'm going to first outline how we would represent the intent context. For an agent to be able to reason about problems, we want to represent the intent content and the actual problem solving process that is occurring. So the intent is essentially what are the goals and desires that I have and how do they change over time. First, we have some background knowledge. This would include sigma that we defined classically before, the state's actions and some successor function. Delta, which is a set of goal transformation rules or functions, and then a interpretation function beta, and a planning or replanning function phi. Phi I'll talk about on the next slide, but this represents the unchanging, for the most part, the background knowledge that you would have to reason about problems, perform problem solving, and to represent a problem. This function beta, and I've described this in previous papers, is fairly novel. The idea is that you want to be able to not just achieve or not achieve current goals, but goals, we want to be able to formulate them and change them over time as needed. So the function beta takes a current state and the current goal and outputs a possibly new goal. It would be goal formulation if the goal parameter was empty. So it would go from a state and no goal to some goal that would be goal formulation. Goal change can also be represented by beta. So goals in this formulation are malleable. They can change over time and go through a trajectory. So we represent this goal trajectory as a sequence of pairs. Pairs of states and goals. So the initial state with the first goal, and then beta might be used to change that into some new goal at some state Si, up into the current state Sj and the current goal. So goals may go through a number of changes over time, and you want to represent that trajectory. In the agenda of a system, we may not be achieving all the goals in our agenda at once. We may or may not. So the goal agenda is some set of actions, including the current goal G sub C. The agenda history then, because goal agendas, if goals come and go, could change. Your agenda could change over time. So you want to be able to represent your agenda history, which is just a sequence of these goal agendas as they change over time. And then finally, the plan, as we defined before, is a sequence of actions, but they go from 1 to, that should be alpha of n, so that, no, I'm sorry, this is the pi sub c is the currently executed plan. So it's alpha 1 through the currently just executed step alpha of c concatenated with the remainder of the plan that I haven't executed yet. So this would be dynamically during plan execution. You have the part of the plan that I've already executed, pi sub c, and the part of the plan remaining, pi sub r. All right. Now, to represent the problem-solving context, we have this function phi that I'd mentioned earlier that's in the background knowledge. This is a planning function or a replanning function that takes a state, a goal, and a currently existing plan or remaining part of a plan, and it outputs a new plan. The planning trajectory then, because of replanning occurs, we want to also keep track of the planning trajectory. So we have a sequence of pairs. Here we have each pair is a goal and the plan that is supposed to achieve that goal. And over time, the plans change given new goals, or just given new world situations that you have to replan for. And finally, the last pair would be the current goal and the remaining part of the current plan. And then finally, we have the current execution episode. And this represents what's been happening during execution of a plan. Starting from some initial state or prior state, we have a sequence of state action, state, executed action, state action, up into the current action, but not the current state in this execution episode data structure. So then finally, we can put this together and have the episodic problem-solving history, which represents the trajectories for the 4 important things that we would want to reason about while recognizing and doing problem solving. That is the goal trajectory, the agenda history, the plan trajectory, and the current execution episode. I'm just going to point out that the background knowledge that we defined earlier is kind of static. You can think of that in some way as long-term memory, where the episodic problem-solving history is in some sense a working memory. It's the representation of the problem-solving context while you're executing plans or doing problem solving. And finally, the problem representation would be this: a situation that limits choice in terms of potential goals or actions. We need an explanation that's in many different forms. It's essentially a set of vertices and edges that causally link current state to those items that limit the choice in some way. So now our current problem is defined as a currently observed action, an expected observation or state, I back up. The currently observed state, the expected state, the background knowledge, the episodic problem solving history, and then the explanation and the new goal. Now for an agent that would be very autonomous, we would actually want the agent to infer the explanation, generate its own goal. And in that case, we might consider the problem solving or the problem representation just being the currently observed and expected states along with this memory, background knowledge, and the episodic problem solving history. So very briefly, I'm not going to go through much of the explanations or with our implementation, but I'll just tell you very briefly on one of the problems, how this would be implemented. We have a metacognitive integrated dual cycle architecture that I've talked about in previous work, MIDCA. It has a action perception loop at the cognitive level and one at the metacognitive level. Given a set of goals, you have 6 phases. Intent chooses a subset of the goals. Plan generates a plan or a solution for those goals. Act iteratively executes them one at a time. Perceive then perceives the changes in the world after the action. Interprets the state of the world. Given the plan, evaluates it with respect to the goals and whether or not you're finished, and it iterates. So act and perceive actually is the 2 phases that change the current execution episode. Interpret involves beta and changes the goal agenda and the current goal. Just the goal agenda and the agenda history. Intend will change the current goal.
Mike, this is your 2-minute warning.
Thank you. And then plan, of course, changes the plan trajectory, and it I'm just going to real quickly mention, I'm going to refer people to the paper, given the time restrictions for this implemented example, but we have mine clearance problems where you have a underwater autonomous vehicle in red at the top. It's a REMUS with a mine outside it. There's a Q route that runs from the left side to the right side. There are a number of ships carrying cargo trying to get through to the right. Within the Q route, or you can think of this as the highway for the ships delivering cargo, there could be two minefields, green area 1 and 2. The agent in the REMUS, controlling the REMUS, is given initially 2 goals to clear GA1 and GA2. The question of mine that it wasn't told about, where it's located in the image here at M1, is that a problem or not? Is it an obstacle to go around, or is it a problem? In our work, we would say that is not a problem. It's more of an obstacle, whereas at GA1 and GA2, we have a mine that does represent a problem because it threatens the ships that go through. So here, I'm going to simply stop and look again at the conclusion that the problem with problems is this classical representation that we're given can be arbitrary and really doesn't say much about why some state what is the problem for a cognitive system and defining it to be limited choice. And here I'm challenging the community to look at that question. It's we have for many years kind of just assumed a simple notation that's been around in terms of initial and goal state. I think we can do much more.
All right, Mike. So there are a bunch of questions in the Slack. I'll start with a question from Tom Henricks. He asks, how does this relate to ill-structured problems? The study of complex systems also deals with these sorts of issues.
So ill-structured problems, I think, is getting at that. The idea is that it's not clearly defined, where we have a set of well-defined problem representation. So this, I think it's Gary Klein talks about wicked problems. It's similar. So sense making is an attempt to try to understand the situation at hand and recognize threats. And so I'm not sure of the particular work that you're referring to, Tom. I know Matthias Scheutz has looked at what's MacGyver problems, and these are starting to represent not just the initial and goal state, but also the context. So I think ill-defined problems is hard to put in terms of a simple initial and goal state, and that's provides, in my mind, some evidence that the classical representation is lacking.
All right, your next question is from John Laird. He asks, does approach assume that an agent must search internally to solve a problem, generate a plan, and then execute the plan, as opposed to searching in the environment, which could be constrained by prior knowledge?
So I would say both. Part of the representation was that current execution episode. So what actions have I done? How is that unfolding in the world? And in fact, the expectations that I have internally, I might have these action models or some schema for the kinds of actions that I have access to. And for instance, I have the idea in an operator representation that there are preconditions and effects. So the effect is a very simple, immediate expectation. When I execute that action, that effect should be observed. When it isn't, that expectation failure or that discrepancy between the observation in the world and what my expectation, my internal expectation was, I think is important. So I would say both.
Okay. Leilani Gilpin says, the idea of the explanation graph is interesting. And she asks, what are the edges and vertices? Or what is an example of what an explanation could look like?
So let me just, I won't talk in detail, but I have a schematic that shows one, let me find it, this second one, this one. Can you still see my screen?
We can currently see the explanation and goal formulation slide within PowerPoint.
Formulation, right. So this is a simplification, but this is essentially 3 explanation patterns, 2 within the larger one of the problem when the Remus discovers the mine between the 2 goal or green in the Q route. The mine explanation just says that there must have been some other ship that laid that mine for me to observe it. It was unexpected. I wasn't told there were any mines to be found there, and that the location of one of these ships in near that mine could cause an explosion, which is a problem in the Q route because they won't be able to deliver their or achieve their goals. And so assume, yeah, so this is a very simple representation they have in, there are states that are being explained. That's E on the right of each of these, actually. There's explanations within explanations here. And you have applicability conditions that are the nodes, and the links are, there's links that aren't shown here that are internal links, but these are causal links. For instance, a precondition enables an action results in some state. Those are the kind, there's more work that I've done. I cite it in the paper on the details for that. And there are alternatives to these kind of explanations. In fact, Matt Molyneux has used explanation that is more similar to Andrew Gordon's discussion yesterday during the first invited talk.
All right, thanks, Mike. Why don't you go on the Slack chat and try to answer